Uh, good. Sorry, I got a little problem today to set things up, but look like it's okay now. Right. So we continue from last time. Try to set up the integral for the distance method, and then the same method for the same region. Right. So we have example 3. So let me begin. To the example 3. Right. Right. So let R is the region bounded by y equal to 2 to the x, y equal to 4, and x equal to 1. And then R rotated about the axis x equal to 1. Now we're trying to find the volume. Right. Now we're going to use both this and washer method, this or washer method, and then the shell method. So let's cut the page in half. Right. Let's try to graph this first. Y equal to 2 to the x power y equal to 4, and then x equal to 1 is the vertical line which we cannot graph using the calculator. Right, 2 to the x, y equal to 4, and then x equal to 1. Right, so let me zoom in. So normally when we hit zoom number 6, that's the standard Windows. -10 to +10, -10 to +10 for x and y. Now we just zoom box, hit enter. Right. So we zoom in that box. Right. And x equal to 1 will be right here. Right. So let me try to draw it. first, let's graph y equal to 2 to the x. I will choose a few points. X equal to 0, 2 to the 0 power is 1. X equal to 1 is 2, and x squared, 2 is 4. Right, so 0 and 1, 1 and 2, and 2 and 4. So exponential function y equal to 2 to the x. And then y equal to 4. And then x equal to 1 as a vertical line. And we're talking about this region. So that one is R. Why it's a little bit glossy on the picture. Anyway. Right, and then the axis of rotation, we will rotate about the axis x equal to 1. So we rotate about this axis. Right. Do the same thing, I will draw this again, but over here we use the shell method. So on 1, 1, 2, 2 and 4. Y equal to 4. And x equal to 1. And we'll rotate about that. Right. So the first thing, this washer. Oh, the question tells us, in the question, on this problem it said, the note over there, it have to tell you on what axis it is rotated about. In this one, R will rotate about x equal to 1. That is in the problem. So the problem always have to tell us where the graph is rotated about. It just happened to be on the edge. Right. So that is in the problem. Don't have to worry about that. Right. Now, first thing about these two is determine which one of them is dx, one of them is dy. Just need to determine which. So this or washer method, this called the slicing, meaning that we're going to slice the axis of rotation, in which case it has to be dx. I'm sorry, it is vertical, so it's going to be dy. And the shell is graphing around the axis of rotation. So if we have the vertical axis like this, and we're going to graph around it, it is going to be dy, going to be dx. I need to slow down a bit. So one of them is dx, the other one is dy, slicing the axis of rotation. That one is vertical, so it's dy. The other one is we're graphing around it, and the width, if we're just rolling around like this, the width will increase horizontally. So this one is going to be dx. So all the variables in this problem is going to be y. All the variable we use on this problem is going to be x. Yes, it is. Yeah, the problem says so. Right, so here we use dy, and this or what's the method? The volume equal to the limit of pi r squared minus little r squared, and here we use dy. Right, and we can see y going from 2 to 4 for that region, so to 2 to 4. However, we have to write everything in terms of y. This is y equal to 2 to the x, so it will not work. Right. So we have y equal to 2 to the x. The inverse of this function, we can check away on both sides, but the inverse of this is x equal to log base 2 of y. Those two are equivalent. So from here, that is equivalent to x equal to log base 2 of y. We're going to use the function in terms of y. This one, y equal to 4, that is okay because there's no x in it. We can just go ahead and use it. Right, now, how do we determine the big radius? And then the little radius. The big radius is from the axis of rotation. Axis of rotation. Go to the edge, the outer edge, the furthest away from the axis of rotation. So that one is the big R. So if we write that, that is the big R, which is bounded on the left by 1, x equal to 1, bounded on the right by y equal to 2 to the x, or x equal log base 2 of y. And so we have to subtract the one on the right, subtract the one on the left. So log base 2 of y, subtract x equal to 1. So from the right minus the left give us the big R. Now the little r from the axis of rotation to the inner edge. And this is why we do not have the inner edge, because the edge is also the axis of rotation. So in this case, the little r is going to be 0. So in particular, we only have the disk. We do not have anything in between. The edge is the same as the axis of rotation, r equal to 0. In this case, this is a disk method. So put that back in. We have v equal to integral from 2 to 4 pi. The big R is this. Little r 0. Or we just drop the 0 and drop the bracket. And that's what we have. So that for the disk method. So when r equal to 0, where the edge of the region is the same as an axis of rotation, let r equal to 0. So that one, this one is the disk method. Not that it's important, but it's like that. All right, now onto the shell. The shell, the formula will be 2 pi r and h, and this one we have the x, and x in this region r, it goes from 1 to 2, so we have the limit. So that's easy to determine, right? Now, what not easy, may not be obvious, is what is big R and what is big H. So the height and the R. So So determine R. To determine R, what we do is we're going to draw a line parallel to the axis of rotation, but have to be in the region. So the region is here, we draw a line parallel to it. So let's draw this line parallel to the axis of rotation and in the region R. So that gives us the height. Right? So the height is that, bounded above by 4 and bounded below by 2 to the x. Yeah, should use red. So that gives us the height, right? Just draw a line parallel to the axis of rotation, parallel to it, and then within the region, we write down the boundary in terms of x, 4 minus 2 to the x. So that is the height. Now, the radius is a little more difficult to determine. So what we do is, we're going to pick a point on the height here, and that point, let's say there's the x coordinate and there's the y coordinate, right? This is the y coordinate and this is the x coordinate. Since we have to use only the x here, so in that case we only use the x coordinates. So this is x. From here, from the y-axis to that point, so that one is x. Right? Just pick a point on the height, and we have x and then y. Since we have x, using the x, we only use x here. Now, the little r is from the axis of rotation to that point. Now, we have the whole thing is x. This distance is 1, so the little the radius here is x minus 1. Give us a very small rotation here. So it's going to be x minus 1. And put it back into the problem. We will have volume from 1 to 2. 2 pi r is x minus 1. And then a height 4 minus 2x. 2 to the x power dx. Right. Now, if we put both of this in the calculator, we should get the answer. Right. Should be the same thing. I'll do that quickly. 2 to 4 pi log base 2 math. Where's the log base? Here. 2 of y. Cannot, it's better to just use x. Minus 2, minus 1, sorry. Right, square. Dx. Right, so we have that much. And now we do the same thing. From 1 to 2. 2 pi. X minus 1. 4 minus 2 to the x. Dx. Yeah, should be the same thing. Right? So, I'll keep this for a minute. Do you have any question on this? Right. So, I got a question. How do we get the inverse? Okay, put that here. So when we have y equal to log base 2 of, y equal to 2 to the x power, what we can do is we will take ln on both sides. When we do that, we can take the x on the outside. And then find an inverse, so we pretty much switch in x and y. So x become y and y become x. So interchange those two. So we have ln of x equal to y ln of 2, and divide by ln of 2 here. So y equal to ln of x over ln of 2. And then the change of basis formula, when we have log base a of something, it is ln of m over ln of a. So with exactly from here turn into log base 2 of x. Yeah. So the log base 2 of x and 2 to the x are inverse of each other. By the way, on the test, I'm not going to ask you anything this complicated. Usually just like x square, or inverse of that is square root, or something like that. Or x cube root. It's not anything this complicated on the next one. Right. So just want to emphasize on the h and r here. Just draw a line parallel to the axis of rotation, and inside the region. From there we can see the bound. Above by 4, below by 2 to the x. It have to be in terms of x. And then we draw the coordinate of any point within. We can pick any point. And then we have x values and y values. We're going to use x because we have x. And then we have x. And then the axis of rotation to that point is just this little part here. And the whole thing is x. Take away 1, we have x minus 1. Right. Yeah. And the inverse. Yeah. solving for y and then switching x and y, so kind of like the inverse. But to just get the idea that we have to find the inverse if we don't have y or x. Right. One more example. E. Yeah, you see the test one review. The question, the function is no nothing fancy, no nothing like this two example. Right, so let R be bounded in the first quadrant. So let R be in quadrant 1 and bounded by y equal to sine x, y equal to 2 over pi x, and R is rotated about the line y equal to 2. Now we find the volume using both this and Watson method and the shell method. Right. Yeah, the graph might be a little bit complicated here. So since we use the trig function, make sure it's in the right mode, the radian mode. So that's good then. Right, let's graph. Y equal to sine x. And then x equal to 2 over pi. If I want to enter fraction, it will be alpha y equal to, the bottom menu pop up, that is the fraction, 2 over pi times x. Sorry. Times x like that. And then the graph. Right. We know it's going to be within this windows. By the way, we can change the windows. Look like we have the sine function and the line intercept at the apex of the sine as the maximum of the sine. So that we know it's going to be pi over 2. So if we don't know about that, let's change the windows. X, let's go from negative pi go to pi. Let's just do that. Sorry. Go to pi. And then each increment, let's say we have pi divided by 4. So hit Windows and then we adjust the window. Right. The sides only go from negative 1 to 1. So let's just say we go from and also we need y equal to 2. So let's go from negative 1 to 3. Right, on the y. So hit Windows and so negative pi to pi over 4, and then that, and then graph. Right. And since each increment is pi over 4, this will be pi over 2. So the intersect is going to be between 0, 0, and then pi over 2 and 1. Right. Where's my ruler? Okay. Right. What's happening with this? So we have pi over 4 each, pi over 2. Right. And then when x equal to pi over 2, sine equal to 1. Sorry, the scale is it's a little off here, but the sine function a little bit. And then, yeah. Yeah, it's not going to be very easy to visualize, kind of skinny region. We know that line intercept at 0, 0. And pi over 2 and 1. So this is 1 here, 2. And the axis of rotation, y equal to 2. We rotate about that line. Right. And we're talking about this skinny region. It is in the first quadrant. That's why we only draw in the first quadrant. Right, so we're talking about this one. Do the same thing here. The line is y equal to 2 over pi x. Right. Clockwise or counterclockwise rotation doesn't matter. I just want to draw that. Right. So we have that region, right? So next, determine, do we use x or do we use y on which one of them? So first, this washer method, the axis of rotation is this. If we slicing the axis of rotation, this is going to be horizontal, therefore it's going to be dx. The other one must be dy. So it's going to be dx. Pi big R square minus little r square. Kind of out of ink on that one. What color is this? Sorry. When it runs out of ink, it's not very easy to see. Yeah, that's completely out of ink. Right, so we have that. For limit for x, it go from 0 to pi over 2. Yeah, much better. So that is dx. And because of that, over here we know that it's going to be dy. And for share method, 2 pi or h. And we're using dy, where y going from 0 to 1. Right, so we can set up both of them. In general, it's going to be like that. Right, so that's the first thing we do. And then when we're graphing around this, we have the increment vertically, so that's dy. Right, now on this side, what is the big radius and what is the little radius? So the big radius is from the axis of rotation to the outer edge. So from here, if I use that color, kind of difficult to see, but let's just, okay, axis of rotation all the way to the outer edge. That is the big radius. And the little radius is from the axis of rotation to the inner edge. That's the little radius. So the big radius is bounded above by 2. This is going to be dx, so we don't need to do anything here. So bounded above by 2 and bounded below by 2 over pi x. So that is the big radius. And then the little radius is bounded above by 2, bounded below by y equal to sine x. And put this back into the integral. We have integral from 0 to pi over 2. Pi 2 minus 2 over pi x square minus 2 minus sine x square dx. Right. So when we draw the region, we know what is bounded by above and below. So that's what we have. Right. So that is the disk or washer method. Or for the shell method, we're going to draw the line parallel to the axis of rotation, and we call that h. Clearly h is bounded on the right by 2 over pi x and bounded on the left by y equal to sin x. The only problem is it has to be in terms of y. So if y is equal to pi over 2x, let me write this. If y equal to 2 over pi x, multiply pi over 2 on both sides, we have x equal to pi over 2y. Right? Multiply pi over 2. Pi over 2 cancel with 2 over pi and go to the other side. So this one is equivalent to x equal to pi over 2y. And y equal to sin x equivalent to x equal to sine inverse y. You will not have anything this complicated. But I just get the idea of we have to find the inverse for one of them, maybe both, like this one. Right? So h bounded on the right by the line pi over 2y and bounded on the left by the sine inverse. Right? So we just draw h, and this happened to be bounded on the right by the line and on the left by the sine x. But we have to write that in terms of y. So that is h. Now, how is the radius? What is the radius? So, what we do here is we just pick a point, any point on the edge here. Let's pick this point then. I said anything on this line is fine. That point have the x and y coordinates. We have the x coordinate from that point to the y-axis and the y coordinate from that point to the x-axis. And we only use y in this case. So this is y. Now, the r is the distance from that point to the axis of rotation. So this is r from the axis of rotation to a point, to the point that we choose on the line. So pick a point on the line, x values, y values. In this case, we need y values. So that's what we have is y. And the distance from the point to the axis of rotation is r. So that is r. So how do we find r? We know y is this much. We know the whole thing is 2, right? So the r is going to be 2, the whole thing, from 0 to 2, minus y. So we have v equal to integral from 0 to 1, 2 pi, r is 2 minus y, and h pi over 2y minus sine inverse y dy. Oh, how do we know if we use dy or dx? The this or the washer method. This is called the slicing method. The axis rotation is y equal to 2. If we slice that, what we have is a little increment. A little increment is horizontal. So that's going to be dx. So just chopping the axis of rotation, that will determine it's going to be dx for the distal washer. And the shell is the other one, will be dy. Or we think about if we're graphing around this axis and just have another one just graphing around this, the thickness of a shell, this, which is this much, the thickness is actually will be perpendicular to it. So what we do is we're going to graph around it. We have one shell, and then we have a bigger shell, and then have a bigger shell, and just bigger shell, just bigger. And every time the width of the shell, or the width of the shell, that is going to be going up like this. That is the width increasing, and the width like that is going to have going to be dy. So that's how we determine dx and dy. That is the first thing we do. Once we determine the dx or dy, just write out the formula for the disc or washer and for the shell. The limit for x and y should be easy to determine. So we determine dx or dy, that's the first thing. Second, the limits. After that, have to find out all the r and the h, or the little r. Right? The example on the test review and on the test is not this complicated. Yeah. Right. Once again, this in washer method, we slice in the axis rotation, and in this case, when we slice that, it's going to be horizontal, and that will be dx. For the shell, it's the other one. Or we form a bunch of shell, and each one of them, the width, it's going to be dy. Right, so checklist. So first one is that dx or dy. That's the first. So the one is, so I should put the number. So first, dx or dy. Second, once we know it is dx or dy, we can write out the limit. Could be for x or y. Right, 3. From then on, we know it's going to be pi r squared minus little r squared. And I'm not sure if we use dx or dy here, so I'm going to leave it blank and just say depends on the problem. This could be dx or this could be dy. And then from there we will write, of course there will be the limit, which we know. Right, 4. The big R is from the axis of rotation to the outer edge. Axis of rotation to outer edge. Little r, axis of rotation to inner edge. So that, and then on the shell method, integral, which we know the limit for now, 2 pi r and h, and we don't know in this case dx or dy, either way. And then number 4, the h first. The h is a line draw a line parallel to the axis of rotation. And then when we do that, because that line have to be in the region R, in the region R, script R. Sorry, I have to change the contrast. It's kind of difficult to see here. I don't know what kind of glossy today with the camera. Is that better? I did not change any setting on the camera, but just a second. Yeah, I think that better. I just changed the exposure of the camera. Sorry. It's the same setting every day, and for some reason today it's a little bright. Right. And when we draw the line like that, we find the boundary. The difference of that is going to be the height. And then 5. For little r. Sorry about that. I should have checked earlier. Right, for r, pick a point on h. And we use either x or y coordinates. And the axis of rotation. To find r. That is too dark. Yeah, but it might be even easy to say I just turn off the line here. Right, so just stick with this. Yeah. Yeah, the only problem is when I write different color, it's not very easy to see. Right. So, with that, let's take 5-minute break. We continue at 9:03 while I try to change the setting. Oh, actually, it works. Yeah, just turn the line off to check the color, make sure it works. Yeah, that's much better than I thought. All right, just turn the light off then. What we are section here is 6.4, the section there. Next we go to 6.5, and then go to chapter 8. The first test will be up to section 8.3. We don't have 8.1, so 6.5, and then 8.2, 8.3. That will be for the test. For now, we don't have to do a lot of drawing in the next section and after that. So a lot of drawing is 6.2, 6.3, and 6.4. Wait, sorry. To just put that part in, so if you want, if it wasn't clear before. See on the tablet, different device, see what happened. So we just keep the line off like this. Even though it's a little bit dark, but I guess it's alright. Even though it's a little bit dark. Just put a little light on. Right, good. So that a little thing's good. I switch to a smaller light. Yeah, it's good. Right. Right. By the way, I'm not a professional streamer, so I don't know the setting and stuff. So if there's something it could be better, just let me know. I play around with this and see if we can improve the quality. Right, length of curve. This one will be a lot easier. We don't have to draw anything. Right, section 1.5, length of curves or arc length. Arc length for y is a function of x. Right. So we have the knot on that side. I'm just going to try to prove this quickly. So a definition. The book used that, call this a definition, but it's more like a theorem. Let f have a continuous first derivative on the interval a and b. The length from the point A, f of a, to the point B, f of b is integral from a to b and 1 plus derivative square dx. Right. So let's prove this quickly. It's actually very easy to prove. Where's my ruler? Good thing we don't have a lot of drawing in this section. So we have a curve. Let's find the length from here to here. Right, so when we're trying to find the length, what we do is, of course, we're going to cut this into small section. That's pretty much what we do in calculus. We do that for very small section. For example, derivative is dy over dx. The integral, we have dx. So as you see, there's always dealing with the small section. And each one, instead of a curve, if we cut that and if we zoom in very close, and that part, it's just going to be a straight line instead of a curve. So I'm going to zoom out, and we have one piece here. It's a straight line. Right, let that the length be s. But since that is too small, let that call ds, the length of one small segment. Right. And the change in y values, that is dy. The change in x values, dx. Since this is the right triangle, ds square is equal to dx square plus dy square. That's simple enough, right? So take the square root on both sides. The length of one tiny segment is equal to square root of dx square plus dy square. Right. And then when we find the length, the arc length, we're going to add all of the length of those. So just do that. From A to B, of course. Dx square plus dy square. Right. What we do now is, again, let's do this again. What I do is divide by dx square that also dx. Divide by dx square and then multiply by dx square. And the limit, of course, from x equal to a, x equal to b. Yeah, the same thing for everything. A to b. Right, dx over dx cancel out, so it's just 1. And both of them had a square. So we bring down inside a square, dy over dx. The dx square here, bring it outside, become dx. And this turn into dy over dx, that is the derivative. And then square root and square cancel out. Should be absolute values. But dx, if we choose, they'll be positive. Then we just have that. So that is the formula, how we derive the formula for the arc length of a curve. Once we know that, we don't have to do a lot of drawing. However, the calculation here is extremely complicated. We only be able to do for some. The sample will be very, very limited. X to the 3/2 on the interval zero to 4. Sorry. Right. So this problem usually very direct. We have the function, we have the limits, and we have the formula. So pretty much just that. So the only thing we need to do is find the derivative. Derivative. We're going to take the 3/2 down. And the original power 3/2 minus 1. 3/2 minus 1 is 1/2. So that is the derivative. Right. Now the arc length. That formula. Right. So this limit goes from 0 to 4. Like I said, the question will give us that. Square root 1 plus derivative 3 over 2 x to the 1/2 and then square dx. So give us integral from 0 to 4. One. Right. 3/2 square of the 3 is 9. Square of 2 is 4. So I have 9 over 4. And then x to the 1/2 square. X to the 1/2 square will be just x. So that's what we have. Just that. Right. So continue. The arc length is the integral from 0 to 4 square root of 1 plus 9 over 4x dx. Right. How do we integrate this? See, this will be just the standard substitution. We'll let inside the square root be u. Can we still see all the different columns? Okay. And so let u equal to 1 plus 9 over 4x. Take derivative and then solve for dx. Derivative is just 9 over 4x. Move the dx over. And then move 9 over 4 on the other side and then divide by x. So pretty much divide by the whole thing here. So du over, the x should be on the top, so we say 9x over 4. Right. I did that on purpose to see if it will actually, yeah, derivative is just 9 over 4. Right. Just to see if you actually cross that or not. Anyway. Substitution. Let u be inside the square root. And we take derivative. It's going to be just 9 over 4. Right. We can move the dx over and then do all kind of that. But if they are two fractions, it's better just cross multiply. So we have du times 4 equal to 9 times dx. Cross multiply. And then divide by 9 on the other side. So 4 over 9 du is equal to dx. So we found that. Dx. Right. Now change the limits. X go from 0 to 4. X equal to 0. X equal to 4. When x equal to 0, put 0 in here to find u. So that's just 1. And then we're going to put 4 in for x. Four and 4 cancel. That gives us 10. So once we do the substitution, the integral, the limit will change from 1 to 10. Those are the limit for u. We have square root of just u and dx 4 over 9 du. Right, there's no x. Oh, we take derivative from here to there. Derivative of 9 over 4x. Derivative of something times x is just that constant. Not just 9 over 4. We take derivative. Right. So take the 4 outside on the top, the 9 outside at the bottom. Integral from 1 to 10 of square root of u du. right? And so this is easy now. The integral. Use the power rule, square root of u to the 1/2 du. Right, we take derivative. I mean, antiderivative of u to the 1/2 is u to the 1/2 plus 1 divided by the same thing. Evaluate from 1 to 10. Right. Divide by fraction is multiplied reciprocal. So 4/9 times 2/3 and u to the 3/2 from 1 to 10. Right. That gives us 8/27 u to the 3/2 or from 1 to 10. Right, we're going to put 10 in and we're going to put 1 in. So 8/27, 10 to the 3/2. And 8/27 of 1 to the 3/2. And 10 to the 3/2 doesn't look like anything nice and even. 10 to the 3/2. Yeah, but 1 to the 3/2 is just 1. So what we have is 8/27, 10 to the 3/2 minus 8/27 times 1, or just that. Right, let's see if we actually get that. Math, option number 9, 0 to 4, square root. Square root of 1 plus a fraction 9/4 x dx. And then we enter this in, and hopefully that is the same. 8/27, 10 cubed. Not the best way to check the answer, but at least forgot the halves, right? Scare me a little. Right, so be that. Right. Yeah, that is the same. So we good. Right, so again, the arc length formula is pretty simple. Integral of 1 plus derivative square in under square root. So square root of 1 plus derivative square, just that. Find derivative and just do that. And the integral. So this we have to use substitution. So let u, most of this problem will involve substitution. So let u equal to inside the square root. And then change the limit, find the x, substitute back in, and that's what we have. So, like I said, on this problem, we don't have to draw a lot, but the calculation is probably one of the most complicated things in this class. I'll find the length of the curve. Even though this looks a bit complicated here, but actually the integral will not be as bad. At least I should say doable. Right, I said only one formula for the arc length, which involves the derivative. So the first thing we'll do is we take derivative. But before we do that, I want to write this as x to negative 1. Write derivative 3x squared and plus 1 over 12. Take down the negative 1 and original power negative 1 minus 1 plus minus 2. Right, so it will be just 3x squared minus 1 over 12 and x to negative 2 if we move to the bottom, x squared at the bottom. Right. Right. Now, of course, when we write like that, that will be a terrible way to do it. So derivative this is the derivative. They obviously not equal to. You should not do that. Right, formula. We have the limits involved with the derivative square, so we have to square this. So either we square it first and then put in the formula, so put the whole thing in the formula and square. I'm just going ahead and square this one first, then put it in here. So just find the derivative and then square the derivative. Right, so derivative square it would be better if I rewrite this as common denominator of 12x squared Let's multiply x squared top here and the bottom. Actually 12x squared top and 12x squared at the bottom. Multiply by 12x squared, that gives us 36 x to the 4th power minus 1. And then we squared. Right, multiply 12x squared on the top, 12x squared at the bottom. That's 36x to the 4th. Right, let's square it. Square the top, square the bottom. And then square up the top. Let's hope there's no typo here, because otherwise it will be very bad. That's square up the bottom. On the top, 36 times 36. Oh, calculator. Right? Minus 36 x to the 4th minus another 36 x to the 4th minus 1. Right. 1296 x to the 4th minus 72. Oh, I see. X. This only works. Oh, negative 1 times negative 1 is plus 1. Right. Then we said that's still complicated. And I agree. That's still. Right. Just put that in here. Maybe something turn up a little bit better. Turn out to be better. Wait, 4 times 4, so that should be 8. Sorry. Right. So 1 plus this mess. So far, I should say that I will not put anything like this on the test. Because the point is just find the arc length. Just demonstrate that you can use the formula. Not that complicated things. Right. So common denominator. What we're trying to do is try to get to the common denominator. So I multiply and divide by the same thing. Right. 144x to the fourth, top and bottom. Right. 144 minus 72 is plus 72. This should be 8. Why keep running 4? Right. Now, notice that one and this one, the only difference is that the top is the minus, this one is the plus. So actually what is the difference of those two is this thing here is the same as that, but with the plus here. Right, so once again, that one, notice that there's a minus here. If we change that to a plus, we change this to a plus. So the point of all of this is when we put things together, the square cancel the square root, and we do not have and we don't have to even use substitution. It will be just that. Where did I forgot the plus one? Yeah, so that will be a plus. If it is minus, when we multiply it out, both of them are minus, contribute to the minus. Now, if we have a plus, if we turn this into a plus, those two will be a plus, and that will be 72x to the fourth with a positive, right? So that's why if we have 144 minus 72 is 72 positive. Since this is positive, that should be a positive. Right, like I said, this have to work out perfectly for this to work, because the integral involving the square root, it will be complicated if inside we cannot use substitution. Right, and now we split this two. No, we don't change a plus. We actually do not change from the minus to a plus. What we did, it just has so happened that when we add in the formula, when we have the plus one here, right? The plus one here turn into 144x to the fourth over 144x to the fourth. And it so happened that 144 minus 72 turned into a plus. Yeah. So it so happened that when we plus 1, we turn from the minus to a plus. So whoever make this problem actually have to do the backwards reverse engineering to make sure that it works out perfectly. Because if we do not have the plus, if we do not have the square here, and the square and square root cancel, the problem will be extremely complicated. So that's why they try to make this perfectly. So when we have the plus 1 here, that plus 1 will turn original minus into a plus just by the plus 1 here. And then we divide 36 divided by 12, 3 x squared plus 1 over 12 x squared from the bottom move to the top. Right. And from here we can just use the power rule. So usually when I learned this kind of problem, and my professor said this is a beautiful problem. I'm not sure about that, but I just say that it is very convenient when we plus 1 and we turn the minus into a plus, and we still have the square. Square cancel the square root. So it is very convenient. Like I said, if we don't have this convenience, the square root will be almost nobody can do. Right? Yeah. So we have that one. Two. No, actually, no, it is not that difficult. In the problem, probably I just take out the 12 at the bottom. That's a little more complicated than it should be. It's just 1 over x, so we don't have to deal with the big numbers. Yeah. But believe it or not, this sort of thing, this kind of problem, that turned me into a math teacher. Especially those kind of problems when you spend the whole night trying to work those problems and finally you find it. Yeah. That's the feeling. It's too bad I cannot put those problems on the test. By the way, no, actually it turned me into a math major. By the way, we only have 2 hours for the test, so I only can put a very simple problem. So pretty much just exactly like we had before, square root of 1 plus the derivative. But this time it is derivative in terms of y. Pretty straightforward. We have the function, and we're trying to find the length between the 2 points. In that case, the interval should be given. Like I said, very straightforward. We have the function from x equal to 0, x equal to 8. Right. Let's try to draw this. Oh, found my ruler. Right. Trying to draw it. Y equal to x to the 2/3. Right, we only go from 0 to 8. Right. 0 to 8. So let's go to the standard Windows, number 6. And then 1. Right, we are given the graph to the point A and 4, and then 0. Right, now the function. Right, so we find the arc length of this function from 0 to 8 and 4. And now, the arc length. Now, we're going to use y later, but first, let's just set up in terms of x. From x, it goes from 0 to 8. Integral of 1 plus derivative dx. Right, so just take derivative of that, pretty much. So that is the function derivative is equal to 2/3 x to -1. Just that. -1/3, sorry. Just that. And then we put it in here. Right. And 2/3 will be 4/9. X to -1/3 give us x to the -2/3. Right. So that's slightly difficult to do. It's not that bad actually. We can do it. Substitution. Right. Just write dot. Suddenly it is doable. What we do instead is why don't we change this into an x as a function of y instead. So if this is the function, what I do is just write this again. We raise both sides to the reciprocal power 3/2. So that's y to the 3/2, and then x. Right. So those are the inverse of each other. So now, if we want to, the arc length will be just 0 to 4. Now we use y values instead of x. And now we have a function of y derivative square dy. So you see, instead of using x, we can also use y, the limit for x, the limit for y. I believe we do a lot of changing from x to y lately. Right. Now, so if x equal to that, derivative x prime equal to 3/2 y to 1/2, and we put this in here. Right, now the question is this better than that? And the answer is obviously, when we do this, y to the 1/2 turn into y. Yeah, so this is a lot more doable than this with the exponent. So in that case, when we switch from x to y, we just turn into that. And by the way, this problem, if we compare to something we did before, actually we just did that, but for x instead of y. So this is example 1b, and we have the answer (8/27) 10 to the 3/2 minus 8/27. And how do we get that? See example 1b. Yeah, because that integral is exactly the integral we did before with x. This time we have y, so it should be the same thing. Yeah, so it shows that sometimes we have to switch from x to y, so we can do it easier. Now I remember that was like 18 years ago when I'm taking calculus, and the professor did ask this question. I did not change from x to y, and I have to work on this one. And actually I got that too, but it take a lot of work to work this one instead of change to y. By the way, if you want to work it, this problem with x, certainly we can do that. The x to negative 2/3, bring it down. I think it's worth just write a few more steps from 0 to 8. and then integral from 0 to 8, common denominator. Multiply that to the top. And then split the square root. Square root of 9 is 3. Square root of x to the 2/3 is x to the 1/3. And then this will work if we would let u equal to 9 x to the 2/3 plus 4. Yeah. Yes, we have calculator back in the day. The TI 83. So they don't have 84 yet. It was 2004, I think. It's also at Israel. I went to Israel too, so I took count 1, 2, and 3 at Israel. So yeah, I remember some. I still remember some of the problem. Usually because that takes me too much time to work on the problem, so I still remember the solution. Anyway, so like I said, sometimes it's much better to switch to y instead of x. Three. Right. Find the arc length. Of the function. On the interval 0 to 2. Right. Write the integral. Then use the calculator. Right. Actually, I think it's time. So let's take another 5-minute break. We'll continue at 10:07. Anyway, I just got an email from the chancellor, and he reminds us that this Friday is Good Friday. So if the campus still open, it will be closed on Friday. So in that case, it is so it's guys, so I have to check the schedule. So certainly even though we are a little bit behind, but when I set up the schedule, I do have a few review days just in case something happen. So certainly we can afford not to have class on Friday. So what we do on Friday instead, we will not meet on you will not have to be here. Right, so there's no class on Friday. What I do instead is, if you have any question on the homework, just send me an email. I will do, and we'll go over some of the review question on the for the test. But we'll not have class this Friday. So I will put the test after Monday. So Monday we finish this, go to chapter 8, and then finish everything for the first test by Monday, and the test will be after that. So yes. Oops. Yeah. So I will have an offline review, and then I post it later. So if you have any question, by that I mean 2 or 3 questions on the homework or the test review, I spend probably about 2 hours to work on those problems, and then I post it later. Monday, when we finish everything, the test, I will make the test available after Monday when we finish all the material. Right, I certainly have to send an email, send an announcement about this, and a lot of other things. Right, back to this. For the arc length, this is a function, and straightforward. We do know the limit from 0 to 2 as well. One plus derivative square. Actually, the test is online, so you can take it anytime you want. Yeah. So I will post the test on Monday, but you can take it anytime you want. Make sure you have 2 hours, and you have two attempts for each test. Just finish before the semester. That'll be good. Right. So the function is x squared. So when we take the derivative, 2x, and just put that in here. And that gives us 1 plus 4x square dx. Right, and you say, well, that looks a lot better than that complicated integral. Look a lot better than this. Even though it look better, but we won't be able to do this one. It will take a lot of things. When we go to chapter 8, in order to do this one, it requires 3 different sections in chapter 8 together. So we have iteration by parts, trig substitution, and then even then still complicated. Suffice to say that if we have to do this by hand after we get to chapter 8, it will take more than one page to do that simple integral. So that's why in this case we set use a calculator to evaluate the integral. So it should be easy, right? So math number 9 from 0 to 2, square root of 1 plus 4x squared dx. Right, so that's approximately equal to 4.65 using calculator. Right. Usually in the real life engineering, that's certainly good enough. Right. We have that next example. I'm not going to even write that out because that takes too much time to write. So if we have this application and we have a function, so we're just going to do this. So what we can do everything on the calculator if we have to. And we enter the function on that side, 630 times 1 minus a fraction x divided by 315 square close. Right, so we enter the function. Right. Now we do the integral. On that case, we have absolute values of x less than 315, meaning x is between negative 315 to positive 315, and then we have square root. Right, we enter the function on the calculator. Now we need the derivative, so I will hit open parentheses first, math option number 8, derivative numerically. That's what I think. So that will do the derivative. We check the derivative with respect to x of the function alpha, calculate y1, where x is x. We close that. So we have 1 plus derivative square dx. This may take some time to do, but should get the calculator, should get the answer. So that is the length of the gateway arc, about 1500 feet, which reasonable. Alright, so what we did was enter the function and then just the integral square root of 1 plus the derivative. To enter the derivative, math number 8. We want the derivative with respect to x, the function. Either you hit alpha and trace or just hit variable, y variable, function, y1, and x. If we do this, it will not work. It only works if it is in the integral form. Of course, it will work too, but that is, you don't know what it is. What is x, by the way? Oh, x is 10. So, when they take derivative and let x equal to 10, that's what we have. Like I said, this has no significance to it. We cannot do it this way. We can put that in the integral where, back to the integral. That integral though, with respect to x, where x goes from negative 315 to positive 315. Right. But other than that, it's not much. Right. I thought we go to the next section, but anyway, set up one more. So write the integral then use calculator. To calculate the arc length of y equal to sine 3x from 0 to 3 pi over 2. Oh, the answer for part B, it is on the calculator. That much. Let me search online if that is the case. Nah, they only give the height. I thought I could find that online, but no. Anyway, it is about 1463 feet. I'm not sure if the function is, how good the approximation is, but yeah. So, arc length from 0 to 3 pi over 2. And just square root of 1 plus the derivative square. Most of this wrong, it will be very difficult to evaluate the derivative. Right. So this is the function. We take derivative. It's going to be sine of 3x is cosine of 3x. And then derivative of 3x, which is 3. And we put that into the integral. On the test, I might only ask you to set up the integral. I'm not sure about that. No, actually, on the test, it will be very simple. Integral to evaluate. But if you only need to set it up, we set it up like this. And on this one, I don't know how to evaluate this by hand. So probably there might be a formula, but it looks complicated. So that's why we use a calculator. But in terms of the arc length, that is the formula. So Just to complete math number 9. From 0 to 3 pi over 2. And then we have square root 1 plus derivative 3 cosine of 3x one more square, right, dx. Most of the problem, the answer is just an approximation using the calculator, because we might not be able to do this by hand. Yeah, but the formula is simple enough. 1 plus derivative square and under square root. Right. So just that. Now we'll go to chapter 8. Right. Now in the next section we will not draw anything. It's just strictly calculation, computation of integration. So chapter 8. Integration. Integration by parts, abbreviate IBP. Right. Before we go there, let's review the substitution method. Right. Substitution. Right. So first, what is u? And usually the substitution we let is inside the parentheses, under square root, on exponents, those sort of things. So that. as u equal to 2x to the 6 plus 1. And we check derivative. That gives us 12 x to the 5th. Right? Move the dx over. And then divide back. And we have dx. So we substitute back into our problem. So that integral equal to negative 3x to the 5th cosine, and that's going to be u, and dx du over 12x to the 5th. Right. Now, x to the 5th cancel out. Negative 3 on the top, bring it outside, constant, bring outside. 12 is a constant outside, but at the bottom. And we just have cosine of u du. Right. Negative 3 and 12 cancel out. We have negative 1/4. And integral of cosine is positive sign. And substitute back in for u. Right. So that is the standard substitution problem. We're going to let u equal to something, find derivative, and so for dx, substitute u and dx. That's what we have. Right, next one. Right. On this one, before we do anything, we can always rewrite this problem as e to x squared at the bottom, move to the top. We change the sign of the exponent. Exponent is x squared. Move to the top becomes negative x squared dx. Right? Now, substitution. I'm going to let u equal to negative x squared here. The reason of that is when the substitution works out perfectly, there should be no more x. There's only u left. Now if we let u equal to negative x squared, the derivative of x squared is x, and that x should cancel with this x. So whenever we let something equal to u, we take the derivative, and that should cancel with the rest of the problem. Should cancel with this x. So that is the good substitution. Right, derivative is negative 2x. Move the dx over. And then divide by the negative 2x. That gives us dx. Now shift, I'm sorry. Right. 5x a negative x squared here that we did. Let them be u, right? So that is u. And then we solve for dx, which is this. Right, so substitute back in, and we have a negative x squared is u, and dx is equal to this. Right. The x and the x cancel out. The 5 is a constant, bring it outside. Negative 2 is a constant, bring it outside. But the 5 stay on top, the negative 2 at the bottom. Still have e to the u du. So that is negative 5 half e to the u du. Integral of e to the u is the same thing. And finally, u is negative x squared. So that is the integral. Next, evaluate. This time we have a definite integral. 0 to 2 to x squared right. So similar to what we have on the previous example. We let something equal to u. Usually inside the parentheses, under the square root, under the denominator, in the angle in sine, cosine, or on the exponent. And whatever we let equal to u, when we take the derivative of u, that should cancel with the rest of the problem. So when we take the derivative of x cubed, we have 3x squared, and that x squared and this x squared will cancel out. So that's a very good substitution. Other than that, it will not work. Right, so take the derivative. 3x squared, move the dx over. And then divide by the 3x squared. And also, on this problem, there are the limits from 0 to 2. When x equal to 2, u equal to 2 cubed plus 1. A plus 1, so it's 9. When x equal to 0, u equal to 2. 0 cube plus 1, which is 1. So you go from 1 to 9. You go to 1 to 9. There's 2x squared, and then square root of x cubed plus 1 is u, and dx is du over 2x squared. Right, works out perfectly. X squared cancel out, and we have 2/3 constant, 2 outside, 3 outside. Two on the top, 3 at the bottom, and then we have square root of u, which is u to the 1/2 from 1 to 9. So 2/3 u to the 1/2, the integral, we can just do the integral right away. U to the 3/2 divide by 3/2. Increase the power by 1 and divide by the same thing. Integral from 1 to 9. So 2/3 divided by 3/2 is multiply reciprocal. So that gives us 4 over 9. U to the 3/2 from 1 to 9. Right. Substitute in 9 and substitute in 1. And 9 to the 3/2, which is 27, by the way. And 1 to the 3/2, still 1. So we have 4 over 9 times 27 minus 4 over 9. One of 4 over 9. So that's a standard substitution. Even definite integral, we still just substitute the limits and still do the same thing. Right. Next, we have this problem. And the question is why substitution doesn't work. First of all, x and then e to the x. We cannot have anything. If we let u equal to x, let's say we have x, e to the x. So if we let u equal to x, then du is just dx, because they are the same thing. So what we did in this problem is and u is equal to x. So what we did was we changed the problem from x to u and accomplished nothing. Right. So let's say if this problem, instead of x squared, it is an x cubed. If it is x cubed, it will not cancel completely with the problem. So that's where integration by parts come into play. That is where the substitution doesn't work, where some x left over. Right. 2. Integration by parts. Let's just write that. It's not that long. Right, proof. It's pretty simple. What we try, let's say we start with the product rule, which is uv prime plus it's not wrong, but u prime v plus uv prime. Right, that is the product rule. What we do now is we take the integral on both sides. So integral, and then integral, and then integral. And then you say why, that should be dx, right? Yes, there will be dx somewhere, but integral and derivative, antiderivative, derivative cancel each other out. Give us uv equal to derivative of that we can write as v du. Sorry, the u prime, so it will be v du and then u dv. And I will just bring one to the other side. Subtract this to the other side. So that is iteration by parts. Right, note. So iteration by parts. The most difficult part in iteration by parts is determine which one is u, which one is dv. So there's a mnemonic there. So let me try this out first. Usually we choose dv, which is easy to integrate. And we can differentiate u. Right. Now, if you remember what we did in this section, sum of the integral that we can. Oh, I blocked the line. Sum of the integral we cannot integrate, so we have to use a calculator. I mean this one. Derivative though, we can always take derivative. So derivative is not a problem. The problem is integral. Sometimes we can't, sometimes we cannot do it. Right. So, but this will help us to choose what is what. So we choose u as, so we'll have I, L, I, A, T, and E. So, because that doesn't mean anything. Or usually, I think some other books, they might use I plate, the L and A, but it should be Liate in that order. It doesn't mean anything. I wish that had some meaning. Anyway, so the L is of course the log. The I is the inverse trig. The A is algebraic expression, which including polynomial or power function and other things. T is a trigonometric expression. And last one, E is exponents. Oh, we did not skip. Yeah, the answer for this is we cannot use substitution because there's an X left in the prompt. I think I briefly talk about that. Right. So after this, we have a note. Let's skip 2 or 3 lines. Now let's skip 2 lines. Make it 3 lines. Get back to that later. Now just jump into an example. I'll go to the next page. Right. Yeah, this is example 3, which is this one. Now, so we're going to do this, and then certainly we're going to need that. But let's divide the page in half because there are 2 different versions of the iteration by parts. There's another way to do that a little more systematically, but for now, just apply the formula. So just do it on the half of the page. Both of them iteration by parts. So first, iteration by parts, we need something to be U, and we need something to be dV. So what to be U? What we choose to be U? Right, it's a log, inverse trig, algebraic expression, trig, and then exponent. So we choose U to be in this order. Do we have any log? Answer is no, so we skip that. Do we have any inverse trig? We do not have that either. So next, do we have any algebraic expression, polynomials, square root, anything like that? And yes, will be an X. So in that case, this will be X. That will be U. Yes, that means we skip 3 lines. When we go back, and I will write something to that later. Probably not today. I think I'm going to write out the note next time. But u equal to x and dv. Of course, if u is that, whatever left is going to be dv. So we need u and then dv. Once we have that, if u is that, what is du? So we take derivative. Derivative is 1. So du is equal to dx. Bring the dx over. So u is x, du is dx. Now if this is dv, to get back to v, we will integrate. And integral of e to the x is e to the x. And then you say e to the x plus c. Actually, it doesn't matter. Just drop the c, the constant there. Alright, so we have u, we have v, we have du, we have dv. Integration by parts. Integral of u dv, v equal to uv minus integral of v du. And then we'll just substitute back everything because this is just u dv. So uv, u, v minus v e to the x du dx. So it is x e to the x, and integral of e to the x is e to the x, and then plus c. Alright, so it is rather straightforward. Right? Yeah, if we know what is u, what is dv, and the rest is simple. 2. 2x plus 1 sine x dx. Right. So what do we let equal to u? Right. Do we have any logs? There will be no. Any inverse trig? No. Any algebraic expression, polynomials are alike. So we have a polynomial here, 2x plus 1. So let that be u. The remaining will be dv. Right. So u equal to 2x plus 1 and v is sine x dx. Right? Now we take the derivative equal to 2 and move the dx over. So du is equal to 2 sine dx. And then this is dv. Dv is sine x dx. So get back to v, let's integrate. Integral of sine is negative cosine. Yeah, u is equal to 2x plus 1. Right. And then when we make that substitution, will be integral of u dv and integration by parts. Integral of u dv is uv minus v du. U 2x plus 1 v negative cosine x minus v negative cosine x du 2 dx. So we have, just put the negative in front, negative 2x plus 1 cosine of x, negative and negative, that positive, cosine of x times 2 dx. Take the 2 in front. And negative 2x plus 1 cosine of x. Integral of cosine is sine. So it's not that, no, dv is equal to sine x dx. It's not v. This is dv. So dv is equal to sine x. So v is equal to negative cosine. We have to integrate. So remember, integration by parts is not u and v. It is u and dv. To get back to v, always have to integrate. Yeah. Right. And after that, it's just derivative and integral. Usually it should be simple. So if we have u, take derivative. If we have dv, integrate. So one derivative, one integral. The u is differentiate, and v to integrate to get back to v. So that's what we have. And then the rest just substitute into the problem, and then evaluate. Right. We run out of time, so I think I have to stop here. And then just a reminder, there will be no class on Friday. I will do an offline review. So if you have any question, homework question or review question, just send that to my email. By Friday, I will check the email and do those problems. By the way, probably in 2 hours. I'm not sure how many questions I have, but I plan to do that in about 2 hours. Once I have the video, I will upload that sometime on Friday. The test will be next Monday. I will post the test next Monday, but you have the whole semester to take it. You have 2 hours to take it, but whenever you want to take it, it's up to you. As long as you take all the tests, all the homework, all the reviews by the final, on the last day of the semester, should be fine. By the way, I'm not sure what to do with the final yet. If the school closed, then we just have to take the final exam online. So right. So I'm going to close the stream now. Do you have any question? Right, obviously I didn't get that email that said the rest of the semester is online. Who did you get that from? But anyway, I'll check. But certainly I will prepare for if that is the case. So we'll take the test online. The final online, just like every other test. Right. So, yeah, I will end the stream now, and have a good weekend. Have a good weekend. See you on Monday.